Okay, this is Algebra 2, Lesson 11. We're going to talk about adding fractions. How do we add fractions? What are the rules? You have to have a common denominator. Once you have the common denominator, you simply subtract and add the numerators. Look at this one, 1/11 plus 5/11 minus 4/11. You have the same denominator. You keep the denominator, and you simply combine the numerators. 1 plus 5 minus 4 gives you 2/11. Simple as that, yes? Same thing can be done if we have variables or letters. So let's look at this one. A over B plus 2 over B plus A plus 3 over B. Right? Well, simply we have three fractions. Don't look at them as crazy numbers just because they have letters. They're not any different. Simply you have A over B, 2 over B, A plus 3 over B. You simply have three fractions. How do you add them? You have to have a common denominator. Are all the denominators the same? Yes. You keep that denominator and you simply add the numerators. You got A plus 2 plus A plus 3. Then you combine like terms. We learned like terms a few lessons ago. So you have A and A. What are the coefficients? They're implied 1. So A plus A is simply 2A plus 2 plus 3 is 5 over B. So it's not any different than a regular fraction. Now what if we got a fraction where the common denominators were not the same? For instance, let's look at this one. What if I did 1/2 plus 3/4? Could I add these together? Not as is, but I could get a common denominator, yes? So I would, and I very highly recommend when you add or subtract fractions, you do it vertically, not horizontally. So I'm going to make this to 4. 2 times what equals 4? It's going to be 2. And when I do the numerator, I must do the denominator, because I have to simply make this what? Equal to 1. Because isn't 2 divided by 2 equal 1? So then I get 2/4 plus 3/4. Now I have the same denominator, so I simply add the numerators, which is 5 over 4, or 1 and 1/4. And we change it out of its form. Or we can leave it. So did I change this number when I rewrote it? It looks different, but I didn't change it. I renamed it because I simply multiplied this by 2 over 2. What is 2 over 2? 2 divided by 2 equals 1. And what is our identity property of multiplication says? When you multiply anything by 1, it's itself. So I'm simply multiplying 1/2 by 1, so therefore I did not change it. It just looks different, so we're just simply renaming it. And this is simply called the denominator rule. Basically, we can also say it's the fundamental principle of fractions or the fundamental theorem of rational expressions when we add letters to it. So basically the denominator rule says if A over B is equal, A over B is equal to AC over BC, because C over C equals to 1, where B and C cannot equal 0. Okay, that is the denominator. And it says the denominator and numerator of the fraction may be multiplied by the same non-zero quantity without changing the value of fraction. So this is called the denominator rule. Or we can think of it as a fundamental theorem of rational expressions. But this is the rule. You need to write it down. If you need to pause this, you may pause it. Okay, so what does that mean? Let's look at an example. Let's look at this one. What if I have K over 2A plus BC over AX squared minus M over AX cubed? Are my denominators the same? No. What is my common denominator? How do I get it? Let's step back and I'm going to show you a little way. The book doesn't tell you. They kind of skip this. I think they go for it. Assume you know how to do it, or I do it later in the lesson. We're going to just stop and do it. Let's take the first denominator. It's 2A. By prime factorization, it's 2 times A. I take the next one and I put it in exponential forms, equals a times x squared. The next one is a x cubed. So it's a x cubed. And you see what I'm doing? I'm putting them in exponential form, in prime exponential form, and I am lining them up by the base. This has a base of 2, the power of 1. There's no other 2's. So it's by itself. These are all a's and these are all x's. So then I look at each column. Since I have 3 columns, I'm going to pull out the base. What's the highest power here? There's only 1, so it's just simply 2. Here, my base is a. They're all powers of 1, so it's just simply a. Here, my base is x. I have a 2 and a 3. Which one's bigger? My 3, so I'm going to pull out a 3. So basically, my least common denominator is going to be, I'm going to write it up here, LCD, this problem is going to be 2ax cubed. Like I said, you want to write these vertically. It helps keep you straight, and it helps keep it neat so you can see what you do, and you're less, not that you won't make a mistake, but you're less likely to make a mistake. So you have just 3 fractions here. So I said my least common denominator is 2ax cubed. What did I have to multiply this by to get to that? To get to this? There's 2 ways of looking at it. Well, I have a 2 and I have an a, so it's missing. So I multiply this by x cubed. What I do to the top, I've got to do the, when I do the bottom, I must do the top because it must equal to 1. So k times x cubed is simply kx cubed. Here, again, this is my LCD. I've got an a. I don't have a 2. And then I have an x squared and x3, so I multiplied it by x. Do you see that? I do the same thing. So you get 2bcx here, ax cubed, but I'm missing a 2, so I'm multiplying this by 2 over 2, or simply 2m. Then we simply combine, you've got all the same common denominators, and you simply combine the numerators. So you've got kx cubed plus 2bcx, don't forget your signs, minus 2m all over 2ax cubed. That's simply your answer. If you have like terms, you can combine them, but we don't have any like terms. Now, you're probably confused. This is where the problem comes in place. Let's look at this problem again. When we did 1/2 plus 3 over 4, well, we can see that we got the common denominator. I showed you how to get the least common denominator already. So we've got it. This one didn't change, so we didn't multiply, so this stays the same. But then we said, how do we get from here to here? Basically, it's 2 times what? Because our numbers are easy to see. We know it's 2. So what we do at the bottom, we do at the top. But another way of looking at it is 4 divided by the LCD divided by the denominator, 2 is 2. We can check it. This times this equals that. Do you see that? Or we can write it this way, which is simply 2. Right here on the side. The same, so basically we took the LCD, divided it by the original denominator, and what's left is what we had to multiply it to get there, right? Doesn't multiplication undo division, division undoes multiplication? That's all it is. This times this equals that. This divided by this has to equal that, or this divided by this has to equal that. It's also your fact family. So those are basic things that we learned a few years ago, or in elementary. So we can't forget that process. So we take the LCD, which is 2ax cubed, and I'm going to write it this way. What's my original denominator on my first term? It's 2a. I can reduce, and I simply get x cubed. Isn't that what I had to multiply the first term by? Yes. Let's do it for the second term. We take our LCD, 2ax cubed, and then it goes back to using your exponent rules. What is my original denominator for my second term? ax squared. My a's cancel out. Another way of writing x cubed is x times x, and x squared is x times x. These cancel, what am I left with? 2x over 1, or 2x. Isn't that what I multiplied my second term by? That's how I got this right here. Okay? Now what about this third term? Again, we take my LCD, 2ax cubed, divided by my original denominator. A's cancel, x's cancel. I'm simply left with 2 over 1, or 2. Isn't that what I multiplied? That's how you get what you multiply it by. Alrighty? It's as simple as that. Now let's move on to inscribed. Let's do one more example. Because you're probably going, this is way too much information, but don't get overwhelmed by it. It's simply fraction. It's simply getting a common denominator. So let's look at M. These are pretty simple, so you can actually see these. Okay, so let's write the denominators. Isn't this an implied one? Yes, it is. So you have k equals k. 1 equals, it's just 1, right? And then a k squared. So k squared, a. Ones, we can take out ones, but it's not going to change it. Here we take out a k, the highest power is 2. Here is a, highest power is 1. So my LCD is a k squared. We multiply these together. That's how you get it. So LCD for this one is a k squared. Alrighty? So now we look at each term. I'm going to write it vertically, just because it helps keep it straight. What do I have to multiply this by to get? We can look at it and we say, I have to multiply by AK, right? Because k times k is square a. So I simply get m AK. Here, I have to multiply by the whole thing, right? Anything times 1 is itself. So it's a b k squared for that one. And then the next one is simply, we're not changing anything because it was exactly the same thing. So it's simply, you keep it just like if 1/2 and 2/4. 4 didn't change, so you don't change the numerator because it's the same common denominator. All right. So now we simply combine them. So you've got a c. Oh wait. Sorry. Here's my problem. MAK minus, you can't forget this minus sign right here, minus AB k squared plus C all over AK squared. That's it. As simple as that. Let's move on to angles. We learned earlier that we said an arc of an angle is equal to the measure of the central angle, for instance, whose radii, we say radii because it's plural. Remember, this is the central angle, this is the arc of that sector, but they're the exact same measure. Yes, we said the arc of a sector is equal to the measure of the central angle. Now let's talk about whose radii cross the circle. Now what's an inscribed, you need to write this down, an inscribed angle. Basically, an inscribed angle is an angle whose sides are inside a circle and whose vertex is on the circle. Now this vertex is at the center. That's not on the circle. This is a vertex. A vertex is where the two radii come together, the endpoint. So let's look at one that is. Let's look at this one. He said this arc is 44 degrees. This is an inscribed angle because its vertex is on the circle and whose sides are inside. Let's look at another one. Let's use the same. Okay, so the measure of an inscribed angle is half of the intercepted arc. This is the arc. It's 44 degrees, so this is going to be 22. This one right here is also going to be 22. Do you see? Because its vertex is on the circle and its intercepts at the arc. If I did this and went through these same points right here, this is also going to be 22 degrees. So the inscribed angle is half of the intercepted arc. Okay, saying that, what does that mean? Let's do one more thing. We said also the endpoints of a diameter of a circle intercepted an arc whose measure is 180 degrees. Thus, any inscribed angle that intercepts the diameter is a 90-degree angle, as we see in the following figure. So what does that mean? Let's look at one. You're like, that doesn't make any sense. Well, it will in just a second. So if I have a circle, okay, and here's my diameter, yes, and I do this, and this is a right, that means it's a right angle, yes? Okay, so later we're going to prove that the measure of an inscribed angle equals half the measure of the intercepted arc. But for now, we're going to content ourselves by using numbers. So let's break this down. So let's look at another one. Basically, here's my diameter, and this is O, and this is A, oops, and this is B. Make this a dotted line, okay, and ABOC, and so this is okay. So let's look at the inscribed angle. B is the arc AC. So this is my inscribed angle, this is my arc. Yes? If they tell us that this is 80 degrees, I know that this is 80 degrees because this is what? The central angle. If I do the dotted line here, yes? And it's equal to the arc. This is a straight line, so I know that this angle plus this angle equals 180 degrees. So this angle right here, 3, has to be 180 degrees. What are the other two angles? Well, because these are radii or radius, they have to be equal. What do we know about triangles? It's an isosceles triangle. That their angles and their sides are related. So this angle would be this one, and this angle would be this one. These two have to be equal. If this is if this is 100, this is 100 degrees, right? Because 100 plus 80, I just did that math. Then this plus this has to equal to 180. So then I simply take 180 and minus 100 gives me 80. Because they're equal, I just simply divide it by 2. So these are each 40 degrees. 40 degrees. It's as simple as that. So let's look at an example. So we just use our information from our sectors. Now we've learned what an inscribed angle is. Let's look at this one. It's example 11.3. It says this is 40 degrees, and it says from here to here is 5x degrees. And we said from here to here is 7x plus 40 degrees. It said find x. Well, what do we know? We know that this is an inscribed angle. Yes, this is vertex here. So this arc is going to be what? We said this is half of that. So this arc is going to be 80 degrees. All right? So what do we know? From here to here, plus here to here, plus here to here is a circumference. We said it all has to equal to what? 360 degrees, because that's what a circle is. So we can simply take this measure, 5x, plus 7x plus 40 plus 80, all equal to 360 degrees. Can we solve? Yes. We simply combine like terms, 12x plus 120 equals 360. It's using algebra now. It's minus 120. 12x equals 240. Divide both sides by 12. X equals 20. It's as simple as that. Because you know, all the way around the circle is 360 degrees. And they gave you from here to here to here. You simply add them together and equal to the 360, and you solve for x. That's all it is. All right, that's it for this lesson. You need to do all the practice problems. We'll see you in class.